digital twinning platform components. Exploiting the power of data for greener last-mile logistics. As explained in Module 3, the LEAD platform automates the execution of a sequence of models that have been integrated to the model library. The models can use data assets relevant to a what-if scenario, and the simulations engine produces the results according to the input datasets. A digital twin comprises a set of virtual models describing the different functions of a physical system. Models come in a variety of programming languages, frameworks, and technologies, too many to be standardized. Trying to fit everything into one platform was a challenge. The solution to making the models compatible with the LEAD platform was to design a method of onboarding models into the platform through containerization. We introduce a well-defined and simple method for packaging models in Docker containers. The diagram shows how the models are packaged into container images that contain all required dependencies. Any necessary data files are passed to the containers through common Docker volume mounting. Further, arguments that need to be passed to the containers can be passed through environment variables or command line inputs. The model can also interact with the streaming data component, which is built on Apache Kafka, to access data ingested from various data sources. Here we see the anatomy of the resulting image of a model implemented using R. To onboard a model into the LEAD platform, we need to follow two steps. First, to add the model metadata in the model library. Second, to make the model compatible with the platform model execution engine. The first step is done through the creation of a Docker file, which is a script that handles the installation of all needed dependencies in terms of third-party software, as well as the file assets that need to be available for the execution of the model. The script contained in the Docker file is specific to the model that is being onboarded. Then the Docker file is built, and the model image is produced and added to a LEAD model image registry. This method applies to most of the models hosted in the models library, excluding the ones that are provided through an API or are made available as executable files. For software as a service models, the recommended approach is to implement a client application that interacts with the actual model through the provided API, and then containerize it as done before. In this way, the platform can execute the model and include it in any model workflow, as any other embedded model. In the case that the model is an executable file, it requires a Windows installation which cannot be properly containerized. The solution is to build a Windows-based REST API application that exposes the functionality of the model, and then follow the approach of the software as a service models. The containerization of the models allows the platform to abstract over the specifics of each model, and treat them in a uniform, standardized way. Now we will present the key technology blocks of the platform. You can see a high-level overview of the different components and their interfaces. Data can be ingested into the platform through an API or as files uploaded by the user, depending on the availability and accessibility of the operational data. The uploaded data are stored in the file system, in reserved directories. The storage subsystem supports different data formats and is equipped with a message broker for streaming data, a distributed file system for large file data, big data stores such as Hadoop, etc. The model library component is a collection of all the models available for the deployment of the digital twins. The library's role is to provide all the necessary metadata, so that the platform can access the model's source, their requirements, inputs and outputs, as well as their execution pipelines and possible model interactions. Through the dashboard, the user can browse through the available models of the model library, create and configure a scenario comprising of a sequence of models, execute simulations, and review the simulation results. The user is guided to the scenario creation through the friendly user interface that allows configuring specific parameters of the scenario, providing data and executing a simulation. The simulation manager is then responsible to orchestrate the execution of the model's sequence. 1. By accessing and retrieving any data necessary for the execution from the storage infrastructure consisting of the file system, the databases, and a message broker. 2. By communicating with the task scheduler to orchestrate the actual simulation execution. 3. By storing and indexing the simulation results to the appropriate storage resources. The event manager is used to feed the models with real-time data. Apache Kafka is used as the event streaming platform, to ingest real-time data streams to the platform. Apache Kafka Connect imports data from external sources. The Kafka cluster is administered by Zookeeper, which keeps track of the cluster's metadata, such as the nodes, topics, partitions, etc. The simulation manager, the event manager and the task scheduler comprise a data-driven dynamic application system, represented here with the acronym DD-DAS, which is the heart of the digital twinning platform. The components of the DD-DAS collectively operationalize the scenarios by linking the models, the input data, the other resources that need to be executed, with the simulation environment that visualize the calculated indicators. At the first step, based on the selected indicators and models, the DD-DAS reads and pre-processes data uploaded from the user or fed through the Kafka topics, and retrieves any additional resources from web servers as requested by the model. The DD-DAS communicates with the model library to access metadata describing the environment and the inputs and outputs of a model. After the data preparation step, the DD-DAS uses the task scheduler to initialize the environment so that the requested model can be executed. Depending on the model's implementation and delivery, this could involve downloading the appropriate container images or retrieving the code from an accessible repository. The DD-DAS uses containerization and virtualization to scale the system, and the task scheduler handles the resources management and monitors the execution of the pipelines. At the end of the execution cycle, the DD-DAS produces multiple model execution outcomes, based on the input parameters and data of the various models in the scenario. These outcomes are sent to the Decision Support System, the DSS, which applies cognitive algorithms to the results of the simulations to select the best scenario based on the parameters and the selected indicator targets. For the lifetime of the scenario, the DD-DAS continues to monitor the data sources at each time step and, depending on established thresholds, reinitiates the simulation scenario pipeline. When a model is added to the model library, the platform knows how to interact with it and how to execute it as part of a model workflow. A scenario is a sequence of models. When users create a simulation scenario and a simulation, they create the definition of the workflow to be executed. The simulation manager is the component responsible for translating this definition to executable instructions that can be passed to the task scheduler. Here is an example of the Hague Living Lab that focused on integrated last-mile logistics with demand-supply matching platforms. In the simulation overview, we can see a workflow comprising 3 different models: the parcel generator, the parcel market and the parcel scheduling model. The task scheduler orchestrates the execution of the model's sequence in this scenario, once we run the simulation. The task scheduler is based on the Apache Airflow workflow management platform. A core concept of Airflow is the Directed Acyclic Graph, in short, DAG. With a DAG, flows, tasks, and relationships between them are defined. In the context of the lead platform, each task corresponds to a model execution and a scenario is represented by a DAG. When a scenario is defined, the simulation manager generates a corresponding scenario DAG. The DAG contains initialization and finalization tasks that are defined by the platform, while the tasks in between correspond to the models defined by the scenario. This is the DAG for the Hague case mentioned earlier, comprising 3 models and 2 connectors. The connector is the function that takes the output of one model and converts it to the correct format as input for the sequential model. The dashboard is the main user interface of the platform and has been implemented with JavaScript, specifically Angular. For the backend, Node.js has been used. At login, the user dashboard provides an overview of the current state of the user's profile, including the available models and scenarios, as well as a brief simulation execution history and status. The user can select a scenario, provide the necessary data to the models, and execute the simulation. At this point, the platform communicates with the model library to verify the input data according to the defined validators and passes a JSON file with the complete information to the task scheduler. Thank you for your attention. Learn how to use the platform in Unit 5.